All right, so we're continuing from the previous video where we're going through chapter 6, thermochemistry. And so what we're doing in this chapter is we're using the first law of thermodynamics to analyze the energy interactions taking place in just general chemical reactions. The type of reactions we've studied so far in this course: reactions in aqueous solution, reactions just taking place in the regular environment or in a lab. What are the energy interactions that take place between a chemical reaction and the environment around it? And we saw in the previous video that we can look at this from the perspective of internal energy as well as enthalpy. And what enthalpy does is, so for a general chemical reaction, there's no work interactions going on for the most part. We're not doing our reaction inside of a piston cylinder. We're just looking at the reaction in general. But there is the idea of the pressure of the environment around the reaction that might need to be pushed out of the way, or maybe the environment pushes in. So there is this pressure volume work to consider. It's not a real type of work in the sense that, again, there's a cylinder, a piston face that's being pushed on so that you're driving a shaft. You know, it's we're still just dealing with a chemical reaction, but there is the environment around it. You know, we're still just dealing with only a chemical reaction. And you can kind of think about, even whenever atmosphere is being pushed out of the way, it's kind of like, even then, just heat's being given off. If it's just pushing the environment out the way, it's still, if you light some gasoline on fire and it explodes, you know, okay, yeah, I guess it's doing pressure volume work, but it's really just all that heat just being released, and then it's pushing the environment out the way. So it's just like a heat transfer. And we saw that even another way to view both delta U and delta H as just heat transfer processes is that if you carry out a chemical reaction at constant volume, the heat transferred, if you measure just the heat transferred, that's equal to delta U. If you carry out a chemical reaction at constant pressure and just measure the heat transferred, then that heat transfer is equal to delta H. In fact, that's why enthalpy was defined. It was defined the way it was defined so that the heat transferred in a constant pressure process would be equal to delta H. And so that's the sense where the definition of thermochemistry is that you're studying the heat transferred in chemical reactions. And it just says heat, because even with enthalpy, you can see it still can be broken down just to Q at constant pressure, like internal energy is broken down to Q at constant volume. So now what we're going to do is we want to learn about the enthalpy of reactions. Again, so the whole goal of this chapter is we have a chemical reaction and we want to analyze the heat transfer in that reaction. We're going to do that through enthalpy. You can still do it with internal energy, but like the standard baseline that we're going to work with is going to be enthalpy, not internal energy. It's enthalpy. And why? Why enthalpy? Because constant pressure processes, that's the most common. That's what takes place in biological systems like the human body and animals and chemistry labs. You know, a lot of those reactions are going to just be at room pressure in the environment. So constant pressure is the most common. And also remember, it doesn't necessarily mean it has to be atmospheric pressure, right? It's any constant pressure. Now, we'll see that the enthalpies that we're going to use most commonly are going to be the enthalpies at atmospheric pressure. But you can see how I'm saying the baseline is going to be, we're going to have enthalpies for chemical reactions that take place at obviously constant pressure because it's an enthalpy, as well as atmospheric pressure and room temperature. That's going to be the baseline. And if you want to change the pressure from there, the temperature from there, or even go to internal energy from there, you can start with enthalpy at 1 atmospheric pressure, room temperature. Okay, so if we have a chemical reaction, reactants to products, the enthalpy of the reaction, delta H reaction, is the difference between the enthalpies of the products and the enthalpies of the reactants. So you add up the enthalpies of the products and subtract that from the sum of the enthalpies of the reactants. That's the change in enthalpy of a chemical reaction, right? So that's what this chapter is all about. We have a chemical reaction. What's the energy change? So the baseline is, what's the change in enthalpy of that reaction? The enthalpy of reaction can be positive or negative depending on the process. For an endothermic process, heat absorbed by the system from the surroundings delta H is positive. For an exothermic process, heat released by the system to the surroundings, delta H is negative. Okay, and so if we come here, it says because most reactions are constant pressure processes, so this saying that it's endothermic or exothermic, that's talking about heat, right? Heat released, heat absorbed. It's implicitly referring to a constant pressure process here. If you have a constant pressure process, then if the enthalpy is positive, then it's endothermic. If the enthalpy is negative, then it's exothermic, right? Because a constant pressure process, the enthalpy, the change in enthalpy will tell you the literal heat absorbed or given off. If it's not constant pressure, though, you can't just look at the change in enthalpy to decide if what was the heat exchange. What I'm trying to do is I want to talk as generally as possible to make sure to give you a full understanding of all of this. And so here they give an example of a bank account, a change in your bank account, and I've given examples like that. Okay, so now it says, let us apply the idea of enthalpy changes to two common processes, the first involving a physical change, the second a chemical change. Okay, so we're at 0 degrees Celsius in 1 atmosphere. That's the freezing point of water. To go from solid H2O to liquid H2O, this is the change in enthalpy. So you can have a change in enthalpy for any process. It doesn't have to be a chemical reaction. So in chemistry, we talk about phase changes as well, right? As long as the internal energy of something is changing, then for the most part, you can assume that the enthalpy is changing. But okay, so this makes sense, right? To melt ice, you need to absorb heat. Like, think about it this way. You could put a flame to ice. You put a flame to it. Right when it melts, you stop. Well, you had a flame on it. You would think you put your finger on it, it's going to be piping hot. No, it just went to like room temperature. It absorbed a lot of that heat. Normally, you put a flame to something and then you touch it, it will burn you. But the ice absorbed a lot of that heat in the melting process. The per mole in the unit for delta H means that this is the enthalpy change per mole of the reaction or process as it is written. That is when 1 mole of ice is converted to 1 mole of liquid water. So this is a bit confusing. I go into more detail on this in the example problem videos. Most concepts in science and physics, when you see something normalized like this, so normalized meaning like a quantity like energy or force or even mass is, say, per kilogram or per volume, so like per cubic meter or like per square meter. For example, force per unit area, newtons per square meter. It's normalized in the sense that if you change the mass or the volume, or you change the amount, or whatever is the unit in the denominator, the per this unit, then the normalized quantity doesn't change, right? So like density, kilogram per volume, so like kilogram per cubic meter, for example. The density of something doesn't change if you change the amount, if you change the volume that you have, right? So like no matter how much steel you have, if you have a large or a small volume of steel, the density is the same either way. It's normalized based on the amount, based on the volume. Well, that's what this seems to look like here, kilojoules per mole. But with thermochemical equations, it's a little bit different. So this can be confusing. And the reason it's set up this way, you'll see as we work more problems, and you'll also see when we get to a later chapter. But like the way it looks here, it seems like if you multiply this entire chemical equation by a constant, say 5, so you have 5 moles of H2O solid gets converted to 5 moles of H2O liquid, then since the delta H is per mole, then you would think, well, even though you multiplied it by 5, it's still just 6.01 kilojoules per mole because it's per mole. If you want the delta H for the reaction, as it's shown here, just multiply by 1 mole. So you get 6.01 kilojoules of heat absorbed. But if the thermochemical equation is multiplied by 5, then just multiply the delta H, 6.01 times 5 moles. And you get, that would be 30.05 kilojoules of enthalpy energy absorbed. Right? That's what you do with density. You multiply by the cubic meters to get the total mass, but the density doesn't change. But for thermochemical equations, you don't look at it that way. So it's a little confusing. It takes a little while to get used to. We're going to see that if you multiply a chemical equation by a constant, so if we multiply this chemical equation by 5, then the corresponding delta H also gets multiplied by 5. So 5 moles of H2O solid converted to 5 moles of H2O liquid, the delta H would be 30.05 kilojoules per mole. So let's look here first. We'll come back to this in a second. As another example, consider the combustion of methane, the principal component of natural gas. So this is a chemical reaction. The change in enthalpy is this minus 890.4 kilojoules per mole. Okay, so we know that when this reaction takes place, this is going to be very hot. Now, right after the reaction takes place, it hasn't given off the heat yet, but all that's eventually going to cool off, right? So the net effect, before you were settled into a certain equilibrium, then you did the reaction, it explodes or it burns. I don't think it's an explosion, and then it settles in again. Now you've got CO2 gas and H2O liquid. But what's happened, this has given off a lot of heat. Okay, but note again, so even the water melting and even this, we're at constant pressure. That does not mean that if it wasn't constant pressure, there's not a change in enthalpy. You could absolutely do that. You could say for a constant volume process, here's the change in enthalpy. But the difference is that wouldn't be equal to the amount of heat given off in the reaction. To find that out, you'd have to go and work with the first law. So same idea. This is a constant pressure process. You can report the change in internal energy, but that's not going to be equal to the heat given off like it would be for a constant volume process. We're talking about heat. Right now, this is thermochemistry. We're talking about the heat given off in chemical reactions. That's what we're analyzing, the heat. Okay, and again, this is the enthalpy in kilojoules per mole. So for every 1 mole of CH4 consumed, it's that many kilojoules. For every 2 moles of O2 consumed, it's that many kilojoules. For every 1 mole of CO2 produced, it's that many kilojoules. That's the idea. You see, they show that here. Okay, so it's per mole in the sense that when you see a delta H or any specified energy change of a chemical reaction, right, like next to the chemical reaction like you see for thermochemical equations, that energy change per mole is for that specific chemical reaction, that specific balanced equation. Not the general equation with any coefficients on the products and reactants, that specific balanced equation. And again, because as I mentioned, and we'll see in a second, if you multiply any entire chemical equation by a constant, then you also multiply that specified energy term by that same constant. It updates to energy change per mole for that chemical reaction. So what is that per mole for? It's per mole of each reactant and each product. Because, as you know, most of the time, you're going to have different coefficients on all of the reactants and products. That's what the per mole is for. So here, for every 2 moles of O2 consumed, 890.4 kilojoules of enthalpy are released. Same idea for every 2 moles of H2O produced, 890.4 kilojoules of energy in the form of enthalpy is released. Now you look at the whole chemical equation as a unit. You don't look at O2 being consumed kind of all on its own, separate from everything. It's all happening as at once. But that's what the per mole is for. Per mole of the reactants, per mole of the products. You can look at them individually, stoichiometrically. The equations for the melting of ice and the combustion of methane are examples of thermochemical equations which show the enthalpy changes as well as the mass relationships. It is essential to specify a balanced equation when quoting the enthalpy change of a reaction. The following guidelines are helpful in writing and interpreting thermochemical equations. So yeah, it's important here. They're saying it's important to specify the states because you could have H2O gas or H2O liquid and the enthalpy is going to be different, right? The difference is going to be the enthalpy of evaporating H2O liquid to H2O gas. 2 moles of H2O liquid to 2 moles of H2O gas as shown here. And also it might be kind of confusing. You might look at this and say, well, what's the temperature? I mean, you're doing this combustion. Obviously, it goes from room temperature to extremely hot. The idea is this is at like room temperature. Then you spark it or whatnot. Then when the reaction is fully complete, this comes back to room temperature. In that process, what's the delta H? Otherwise, it's not constant temperature. You would have to factor in what is the temperature here. You'd have to specify this is room temperature, this is this, this is this amount of heat. That would be a different state, right? You'd have state 1, state 2, but typically we're talking state 1 and state 2 are at the same temperature. Okay, if we multiply both sides of a thermochemical equation by a factor n, then delta H must also change by that same factor, right? If you just multiply the entire chemical equation by a constant, then you have to multiply the delta H by that constant, or the delta U, or whatever the energy is. Okay, and here they're talking about you can have a chemical equation and you can flip it, and when you flip it, you just multiply the delta H, or the energy amount, by a -1. So here, this H2O solid to H2O liquid was 6.01. If you flip it, it's -6.01. And if you flip it again, it goes back to 6.01. Okay, a comparison of delta H and delta U. This is interesting here. What is the relationship between delta H and delta U? To find out, let us consider the reaction between sodium metal and water. Okay, 2 moles of sodium solid plus 2 moles of liquid water. We know that the alkali metals are very reactive with water. They're so reactive they can displace that hydrogen, right? That metal can displace that hydrogen easily. Gives 2 moles of NaOH aqueous plus H2 gas. And this is the enthalpy of this reaction. The thermochemical equation says that when 2 moles of sodium react with an excess of water, 367.5 kilojoules of heat are given off. Note that one of the products is hydrogen gas, which must push back air to enter the atmosphere. Consequently, some of the energy produced by the reaction is used to do work pushing back a volume of air against the atmospheric pressure. To calculate the change in internal energy, we rearrange equation 6.8 as follows. Right? So they want to calculate the internal energy. So we need to subtract out that P delta V work. And all they do is they say, okay, if we assume the temperature to be 25 degrees Celsius and ignore the small change in the volume of the solution, we can ensure that the volume of 1 mole of H2 gas at 1 atmosphere and 298 Kelvin, because that's what you're assuming you're conducting the reaction at, is 24.5 liters. So that constant pressure times that delta V, because the delta V before was 0. There was no gas before, right? Like you think about it, the control volume before your control surface, your thermodynamic surface, was surrounding this solid in sodium and liquid water. Then this gas comes out of nowhere. It doesn't stay in the solution or anything. It could stay in the solution, but it comes out of the solution. All we need for this work term is the delta V, the change in the volume. Well, this gas came out of nowhere. So that delta V is just, okay, it's the gas is 24.5 liters. So P delta V, 2.5 kilojoules. So the internal energy, you just subtract 2.5 from minus 376.5. Now it's minus 370. Okay, now what's interesting about this is really not that much, right? And furthermore, in addition to that, we ignored the small change in the volume of the solution. And so what you realize is that for any chemical reaction that doesn't involve a gas, the volume changes in the control volume are going to be very small, right? So let's say a gas wasn't given off here. Let's just assume a hydrogen gas wasn't given off. You have this solid sodium plus the liquid water. That's the initial volume. You get this NaOH in solution, but this is sodium, the sodium ion, compared to solid sodium. So it's like that valence electron was given off to make an ion, right? But I mean, that's on the atomic scale, that's really small changes in volume compared to like a gas being produced, a gas shrinking or expanding. Any situation where a reaction happens and like water needs to be pushed out the way, so like the total volume is, you're trying to expand the water. Water is very incompressible. So are solids. The volume, if you break down the actual volume changes, it's going to be really small. But don't get me wrong, it's still there. And you have to calculate you have to carefully look at the reactants and the products and see, okay, what's the change in volume? Look at the atmosphere around, like the sodium metal that converts to an ion and whatnot. If you got water pressure, whatever, see what's that pressure moved over a distance. And you would calculate it. But that delta V for the case of solids and liquids is going to be so small, it will be pretty much negligible. But for any situation involving a gas, you want to make sure it's not negligible. So just to give an example, let's say you have a gas It's a full gas. So before you've got the control surface is the gas. Let's say all of that gets converted to solid. It's like the opposite of condensation. Well, then what happened? You had an initial volume and then a final volume, the volume of the solid, and then that constant pressure. So that would give you a sense of the enthalpy. Now, you wouldn't have that in a problem because that's like kind of associated with the enthalpy of whatever is the opposite of condensation. But I'm just trying to give you a sense of the idea of that pressure volume work being done with gases. Gases can change. You have your control surface on the reactants or products. If there's gases involved in any way, there's a chance that control surface really changes a lot with that constant pressure on it. Okay, calorimetry. Calorimetry is the measurement of heat changes. This is really powerful. Calorimetry is really powerful. We can accurately measure heat changes, the amount of energy exchanged due to heat. This is how we determine, for example, the enthalpy of chemical reactions. This is how we can measure the heat given off. In a constant pressure process, you can measure the enthalpy change for a reaction, or if you do it at constant volume, you can measure the internal energy change. You can measure that heat transferred. So how does calorimetry work? First, you need to understand what specific heat is. The specific heat of any substance is the amount of heat required to raise the temperature of 1 gram of the substance by 1 degree Celsius. So the units are energy per mass temperature, joules per gram degree Celsius, for example. The heat capacity is the exact same thing, it's just not per gram. So in other words, water has a specific heat, but then a bathtub filled with water versus a swimming pool filled with water, the swimming pool has a higher heat capacity. It can take on a lot more heat if you needed to. It could be like it's more of an effective heat sink. It could absorb more heat than a bathtub, but the specific heats of both are the same. Okay. And so all the heat transfer is, to calculate heat transfer, you need the specific heat of something and the change in that something's temperature. The specific heat or the heat capacity, however you want to look at it, you multiply specific heat or heat capacity by the change in temperature of that substance, and that's going to tell you the heat transferred to or from that substance, that body. That's it. Okay, so we've got constant volume calorimetry. This is called a bomb calorimeter, because how they do it is they'll have this chamber here where they put a substance in. This could be a chemical reaction, or it could be just like a tomato, or, like they'll measure like the energy content of foods this way. Well, actually, I've heard that. I talked to some chemists, and apparently, so we're going to see we've got constant volume calorimetry and constant pressure calorimetry. We're about to look at constant pressure calorimetry in a second. And all they talk about with constant pressure calorimetry is like a styrofoam cup. It's this really cheap device. And then here, this looks a lot more expensive, but apparently they've got really advanced constant pressure calorimeters, which you would think that would be the case because you want to measure enthalpy more than you want to measure internal energy. But I think you could easily, even if you got the heat exchange here, you could easily convert that into enthalpy. But also, I think that you probably want to measure, like for foods, you want to measure the internal energy. Right, you want to measure the exact energy inside that food content, not the enthalpy. There's no work. What's the literal internal energy inside of that food? That's the amount of calories in that food. So maybe that's why they use constant volume calorimeters to calculate the energy content, the absolute actual internal energy content within things. But anyway, so you've got this chamber here, and it's inside of this other chamber, and around here is all water. They pump a lot of oxygen in, and you can imagine because they want to burn. They want to burn this. They want to burn it completely, and so you have an excess oxygen more than you even have in normal atmospheric conditions. So you can burn like a tomato. You can burn anything. It's so much oxygen in there you can burn it. They spark it. It burns. Heat gets transferred through the container into the water, and you measure the delta T of the water, and from there you can calculate the amount of energy that or heat that was given off by the substance. But first you have to calibrate the calorimeter. What they do is they first burn something where they know the exact energy content, and then with the delta T, they know the heat capacity of this entire system, right? The heat capacity is going to include like the net heat capacity of the chamber, of this mini chamber in here, of the water, of kind of everything as a whole. But it doesn't matter. All you need to do is, if you know the energy content of whatever your calibration piece is, then just whatever the delta T is, you'll just calibrate that with the known energy content that was given off. Now you've got the heat capacity of your calorimeter. You can then put something of unknown energy content and get its internal energy. Okay, constant pressure calorimetry. It says a simpler device than the constant volume calorimeter is the constant pressure calorimeter, and they show this two styrofoam cups as a good enough insulator. You can imagine you need just enough insulation for a short period of time for you to take your measurement. It doesn't have to be this like infinite insulation, but this is at constant pressure, right? And then they put like a reaction in aqueous solution. It stirs it up, and they measure the delta T of the water. But again, I've heard that there's more advanced constant pressure calorimeters. But you could also imagine a constant volume is valuable from the standpoint of you're getting the literal and the internal energy content, the true energy content of something. You know, there's no pressure work complicating anything. It's the actual energy content. So, you know, to me, what that means is like foods. That's how they determine the calories in foods. You don't want the enthalpy of the food. You want the internal energy. Don't quote me on that. I'm making assumptions. I'm not a professional chemist. Okay, heats of some typical reactions measured at constant pressure. Heat of neutralization, heat of ionization, heat of fusion, heat of vaporization, right? So you can measure with a constant pressure calorimeter, you can measure these energies, because this is just changes in energy. Going from H2O solid to H2O liquid, measure the heat change, the heat given off. Standard enthalpy of formation and reaction. Okay, so you can see that we want to be able to find the enthalpy of a reaction, but we need a standard way to do this easily. We don't want to have to, for every single chemical reaction that's in existence, it must be put into a calorimeter to find out the heat of the reaction. There's got to be a more systematic way of finding the enthalpies of reactions. Well, what they do is they determine the standard enthalpies of formation of substances like CO2 or, you know, of the known substances. And then from there, you can take any chemical reaction, and if you know the enthalpy of formation of all of the substances, then you can use a method to calculate the enthalpy of a reaction without having to take that unique reaction and put it into a calorimeter. All you have to do is tabulate the enthalpies of formation of all the different substances that we work with. Then you can take any reaction you want and use that table to find the enthalpy of the reaction. So what they say is the standard enthalpy of formation of a substance, so of CO2 or of H2O, this is the enthalpy of formation of that substance at 1 atmosphere and also room temperature. This is the baseline. This is the most common scenario. But if you need to change that enthalpy to a different pressure or a different temperature, there's ways you can do that, and that's what you get into in thermodynamics classes. But we're not going to do a lot of that in this chemistry course. We'll either be working at 1 atmosphere and room temperature, or if the reaction is not at standard conditions, they'll just give us the enthalpy. But there's ways you can have your table of enthalpies of formation at 1 atmosphere and room temperature, and then from there, if you need to change the pressure and say, okay, what's the enthalpy though at this pressure or this temperature, you can easily do that. Okay, so this superscript, this like almost degree looking superscript, that means standard state, 1 atmosphere, and should be room temperature as well. And the F stands for formation. The idea is it's the enthalpy to form that substance. The enthalpy needed to form that substance. However, we can't measure absolute energies, right? We can only measure energy changes. So what we do is we say any elemental form of a substance, the most stable form of the elemental form of a substance. So, O2 and O3 are both elemental forms of oxygen, but O2 is more stable. So it's not even the element itself. Like, it's not like O by itself is it's not just the element name. It's the most stable form in nature, the most stable elemental form. So that would be O2, not O3 or not just O. The enthalpy formation is defined to be 0. That's not truly the case, right? It took enthalpy to form O2 from just two separate oxygens. And I don't know if it could be positive or negative enthalpy. It took enthalpy. If you combine two oxygens at constant pressure, there should be some heat given off or taken in. But what we do is we define that as 0. And everything else is referenced from there because that's the most stable form. We can easily make other reactions happen, all the reactions we want that usually don't involve the breaking down of a stable form, the most stable form of an element. We can measure those energy changes. So the reference, that's why those are the reference. It's the same idea as like we say sea level is 0 in height. And then everything else on Earth is measured, valleys and oceans and mountaintops. The heights are measured relative to sea level. But is like sea level the absolute 0 height of the universe? I mean, probably not really. But it doesn't matter for the sake of what we're using those heights for. We can say that, right? So we say that the enthalpy of formation of carbon as graphite is 0, but carbon as diamond is 1.90 kilojoules per mole. The enthalpy of formation of O2 is 0, but the enthalpy of formation of O3 is 142.2 kilojoules per mole. Positive. So heat is absorbed. If the process to make O3 from O2 is at constant pressure, then the heat there's going to be 142.2 kilojoules of heat absorbed per mole of reactant or product. Same thing with diamond. If you made diamond from graphite, then at constant pressure, then 1.90 kilojoules per mole of reactant or product would be absorbed. Now, I don't know how these are made. Maybe you first, take O2 and break it down into, and put a lot of energy in and break it down into into like two O2 minus ions, and then O3 is made from that. It probably takes some advanced methods to measure, okay, well, what's the enthalpy of formation to break up O2 into like two oxygen ions or whatever, or to two stable oxygen elements, right? So like breaking O2 into two stable oxygen elements, it would be hard to do, and you'd measure the enthalpy of formation of just oxygen from O2, and then O3 would be produced, so you'd have a change in enthalpy going from just the O elements to O3, but the net effect would be you're going from O2 to O3. I'm just trying to give you a sense for, it's not like you can't break down O2 into like O2 minus ions, and you can't measure the enthalpy change associated with that. I mean, that sounds like it's more difficult to do than just mixing something and letting the reaction happen. But you can see why that sea level reference, that 0 point, would be the standard enthalpy of formation. So not just the enthalpy of formation, but the standard enthalpy of formation. So room temperature and pressure of the most stable form, elemental form of something. So, okay, you can see that. So with this definition, what you do is you use calorimetry to figure out the enthalpies of formation of all kinds of elements and compounds. Not of any chemical reaction, just the element or compound. And once you have those tabulated, you can come to a chemical reaction, and you can use those values to calculate the enthalpy of a reaction. You don't have to select for every single chemical reaction. You have to go find that unique chemical reaction and look up what its enthalpy of reaction is. you just use enthalpies of formation and find it. What you do is you say, like, it's C times the enthalpy of formation of C plus D times the enthalpy of formation of D minus, so you add up these enthalpies of formation, and it's per mole, so you multiply by the coefficient and subtract that from this. And that's the delta H of the reaction. If the reaction is taking place at room temperature and pressure, then you can use the standard enthalpies of formation. If not, then you'll have to adjust from the standard enthalpies of formation. Okay, so we're going to work a bunch of examples of calculating the enthalpies of a reaction with using enthalpies of formation. They show the direct method here, and then the indirect method is how you can, you can flip reactions, and or you can, so you might want to find out the enthalpy of a certain reaction. If you happen to know the enthalpies of other reactions, you can try and like add this to other reactions to arrive at the reaction you're looking for. Okay, so they're looking for the enthalpy of this reaction. So they start with this reaction where they know the enthalpy of the reaction. They add to that, well, this here, this reaction. Well, they don't, okay, well, no, they first obtain this reaction here. And so these two aren't the same. This is CO2, this is CO. They flip that second reaction, and they also flip the enthalpy of the they put a positive instead of a negative. Then they add that initial reaction to the flipped and get the enthalpy of the reaction they were looking for. So we're going to work a bunch of examples on using enthalpies of formation and also potentially reactions like this to find enthalpies of reaction. Okay, heat of solution and dilution. Although we have focused so far on the thermal energy effects resulting from chemical reactions, many physical processes such as the melting of ice or the condensation of a vapor also involve the absorption or release of heat, right? As long as the internal energy is changing in something, then there's going to be heat coming in or out. That's kind of what we're doing in chemistry. It's chemical reactions, but it's more of we're analyzing if the internal energy of something is changing. That's kind of chemistry happening, right? A change of phase, that's internal energy changing, even though it's not a chemical reaction. Enthalpy changes occur as well when a solute dissolves in a solvent or when a solution is diluted. Interesting, right? So enthalpy changes occur when a solute dissolves in a solvent or when a solution is diluted. Well, when you dissolve a solute in a solvent, that's usually at constant pressure. So what they're saying is that if there's an enthalpy change, there's heat coming out or going in. Same thing when you dilute a solution. Okay, the heat of solution, or the enthalpy of solution, is the heat generated or absorbed when a certain amount of solute dissolves in a certain amount of solvent. And, just to make it clear, so that they're implying constant pressure process. If it wasn't constant pressure, if you were dissolving a solute in solution and it wasn't constant pressure for some reason, there would still be a change in enthalpy, but you couldn't tie that directly to the heat transfer. You'd have to find those terms in a roundabout way. But the quantity delta H solution represents the difference between the enthalpy of the final solution and the enthalpies of its original components before they are mixed. That is solute and solvent before they are mixed, right? So your system is the solute and the solvent before they're mixed. After they're mixed, now they're in solution, they've been dissolved. What was the heat transfer just for that process? If at constant pressure, that's the enthalpy of solution. Okay, so they want to consider dissolving NaCl, solid NaCl in water. We already know what's happening here. The NaCl, that three-dimensional network, that ionic compound, all the ions break off and are dissolved. They're hydrated into the water. They're surrounded by water molecules. So going from this configuration, this solid NaCl, to these dissolved ions, what is the change in heat, the heat given off? That's the delta H of solution. Okay, now you could just use a calorimeter to measure this, but they want to do an exercise here. They said, for the sake of analysis, we can imagine that the solution process takes place in two separate steps, illustrated in figure 6.11. First, the Na plus and Cl minus ions in the solid crystal are separated from each other and converted to the gaseous state. Okay? Now you can evaporate NaCl. It's going to take a lot of heat, but you can see how much heat is absorbed to evaporate NaCl. And what happens? You have Na plus gas Cl minus gas, we're kind of similar here, right? We're almost halfway there. And so if you know the energy that it took to evaporate NaCl, which you could determine that, now you need to know what's the energy needed to hydrate, to stabilize these ions in water. The energy required to completely separate 1 mole of a solid ionic compound into gaseous ions is called lattice energy. And again, so they get some big machines that can transfer a lot of heat, and they can determine lattice energies. That's how they can determine it. They evaporate, salt. The lattice energy of NaCl is this. In other words, we need this much heat to break 1 mole of solid NaCl into 1 mole of Na plus ions and 1 mole of Cl minus ions. Next, the gaseous Na plus and Cl minus ions enter the water and become hydrated. This isn't, they say this, they put this in quotes because this is not literally what's happening. It's a mental exercise. But this is legitimate though. Like you're going to get, you can find out the energy, the enthalpy of solution in this way, in a roundabout way like this. You can do this. This is legitimate. So what is the energy involved in going from these gaseous ions to these ions in the aqueous state, these hydrated ions? This is called the heat of hydration. This is not the heat of solution or the enthalpy of solution. So the enthalpy of solution is the lattice energy plus the enthalpy of hydration. This is going to be negative. And there you go. So 788 kilojoules per mole minus 784. The delta H of solution here is 4 kilojoules per mole is absorbed. Okay. Now they talk about the heat of dilution. Similar idea. Whenever you dilute a solution, heat's given off in a lot of cases, and sometimes a lot, and you have to be careful. They talk about you have to be careful. Chemists have to be careful that you don't just go dilute something because a lot of heat could be given off or absorbed. It says generations of chemistry students have been reminded of the safe procedure for diluting acids by the venerable saying, "Do as you ought to, add acid to water." So I guess instead of diluting, add acid instead. So like start with a very dilute solution, I'm guessing, and then you can add acid as needed.